What if everything we think we know about the beginning of the universe is just wrong? Picture this: the cosmos, vast and enigmatic, holding secrets that defy our wildest imaginations. We've all heard the Big Bang Theory, the explosive birth of everything. But what if that's only one piece of an infinitely stranger puzzle? Today, we're diving into the deepest corners of space and thought to uncover 25 bizarre, mind-bending theories about how all this everything might have really begun. Some are so outlandish they sound like science fiction. Others tease at truths so profound they might just rewrite reality itself. Think about the stories we tell ourselves to explain the unknown. Ancient civilizations saw gods weaving the stars into existence. Modern science points to cosmic inflation and quantum fluctuations. But what if the truth is stranger than all of it? What if our universe is just one bubble in an endless froth of multiverses, each with its own laws of physics? Or consider this: what if time isn't linear at all and the universe didn't have a beginning, just an endless cycle of rebirth? These aren't just wild guesses. They're serious theories proposed by brilliant minds, each with its own eerie evidence and tantalizing possibilities. This journey isn't just about satisfying curiosity, it's about stretching the limits of what we believe is possible. From holographic universes to cosmic eggs, from simulations to divine blueprints, we'll explore ideas that challenge everything we take for granted. And here's the thing: even if only one of these theories edges closer to the truth, it could change how we see existence itself. So buckle up. By the end of this, you might not just question the universe's origins, you might question reality. Ready to have your mind blown? Let's begin. First on our list is a theory that sounds ripped straight from a sci-fi blockbuster. But what if it's not fiction at all? The simulation hypothesis suggests our entire universe, from the swirling galaxies to the coffee in your cup, might be nothing more than an ultra-advanced computer program. Think about the video games we play today, with sprawling digital worlds and characters who seem almost alive. Now imagine a civilization billions of years ahead of us, capable of crafting a simulation so flawless, even we can't tell it's not real. Philosopher Nick Bostrom laid out a chilling case for this idea. He argues that if any civilization could reach the technological peak to create such simulations, they'd likely run countless versions, meaning the odds we're living in the one true reality are astronomically low. And it's not just philosophers in ivory towers. Elon Musk has famously said the chances we're in base reality are 1 in billions. Even cosmic glitches, like particles behaving differently when observed or déjà vu moments, have sparked debates. Could these be tiny errors in the code? But here's where it gets wilder. If the simulation theory holds, then every law of physics, every star, every thought you've ever had could just be lines of code written by some unfathomable intelligence. It's a humbling thought, and maybe, just maybe, a clue to why the universe seems to follow mathematical rules so perfectly. After all, the best simulations run on logic. So next time your Wi-Fi cuts out or déjà vu hits, ask yourself, is this just a bug in the system? What if the universe we experience, every star, planet, and even our own bodies, isn't truly three-dimensional at all? Welcome to the holographic principle, a theory so radical it suggests reality as we know it might just be an incredibly detailed illusion, like a cosmic projector casting shadows on the walls of existence. Imagine peeling back the layers of the cosmos only to find everything: your memories, the Milky Way, even time itself encoded on a flat, two-dimensional surface at the edge of space. It sounds like something from a futuristic thriller, but this idea has roots in some of the most cutting-edge physics of our time. The concept gained traction thanks to physicist Leonard Susskind, who wrestled with one of science's great mysteries, the black hole information paradox. When matter gets sucked into a black hole, does it just vanish? Quantum mechanics says no, information can't be destroyed. So where does it go? Susskind and others propose that all the data about what falls into a black hole isn't lost. It gets smeared across the event horizon like cosmic graffiti, preserving it in 2 dimensions. Here's the mind-bending leap. If that's true for black holes, could the entire universe work the same way? Could the 3D reality we experience just be a holographic projection from a hidden 2D surface we can't see? Scientists didn't stop at speculation. Enter Fermilab's holometer, an experiment designed to hunt for the pixelated nature of spacetime itself. If the universe is a hologram, there should be a limit to how finely reality can be divided, like the graininess you'd see if you zoomed in too far on a digital photo. The holometer fired lasers down long tunnels, searching for tiny, jittery fluctuations in space that might betray its true holographic nature. While the results haven't confirmed the theory yet, the quest isn't over. If proven, it would mean every action, every thought, every moment in history is really just information etched on some unimaginably vast cosmic hard drive. But why does this idea matter? Because it forces us to rethink the very fabric of reality. If the universe is a hologram, then free will, time, even consciousness might just be emergent properties of a deeper, simpler system. Like how the characters in a video game think they're making choices when really they're just following code. It's a humbling thought. Maybe we're not the builders of our destiny, but actors in a cosmic show with the real story unfolding somewhere beyond our perception. So the next time you gaze at the stars, ask yourself, are you looking at the universe or just its shadow? What if the Big Bang wasn't a one-time event, just the latest explosion in an endless cosmic heartbeat? Enter the cyclic universe theory, where the cosmos doesn't have a beginning or end, only an infinite loop of expansion and collapse. Imagine the universe as a phoenix, dying in a fiery crunch only to rise again from the ashes over and over forever. This isn't just poetic imagery, it's a serious scientific proposal championed by legends like physicist Roger Penrose, who reimagined time itself to make it possible. Penrose's version, called conformal cyclic cosmology, twists our understanding of reality in a fascinating way. Normally, we think of the universe's death as a cold, empty fade into darkness, the so-called heat death. But Penrose suggests something wild. When the universe expands so far that everything dissolves into pure energy, that state becomes mathematically identical to the conditions right before the Big Bang. In other words, the end of one universe could literally be the birth of the next, with no boundary in between. Time loses all meaning at these extremes, allowing the cycle to reset seamlessly. Now here's where it gets eerie. Penrose and his team claim to have found fingerprints of previous universes in our own. They call them Hawking points, strange, circular patterns in the cosmic microwave background, the afterglow of the Big Bang. These glowing spots, they argue, could be the final bursts of radiation from supermassive black holes in a universe that existed before ours. Think of them as cosmic echoes, whispers of a world long gone, imprinted on the fabric of our reality. Critics aren't fully convinced yet, but if true, it would mean our universe is just one page in an infinite cosmic storybook, with countless chapters written and rewritten across eternity. But why does this matter? Because it shatters the idea of a linear timeline. If the cyclic model holds everything we know, every galaxy, every life form, every moment of history has happened before and will happen again in some form forever. It's a humbling thought. Maybe the dinosaurs weren't the first to walk the earth, and maybe humans aren't the last. The universe might not have a grand finale at all. Just an endless, rhythmic dance of creation and destruction, where every ending is a new beginning in disguise. Imagine a cosmic Russian nesting doll, a black hole so dense and powerful that instead of ending reality, it births an entirely new one. This is the black hole birth theory, a spine-tingling idea that our entire universe might just be the offspring of a colossal collapse in another, long-forgotten cosmos. Forget the Big Bang's fiery explosion. Picture instead a silent, invisible rupture in space-time, where the crushing grip of a dying black hole becomes the cradle for a brand new existence. The theory traces its roots to physicist Lee Smollen's provocative Fecund Universes hypothesis. Smollen dared to suggest that black holes aren't just celestial vacuum cleaners, they're cosmic wombs. Every time a black hole forms, he argued, the incomprehensible forces inside could trigger a quantum bounce, a rebound so violent it spawns a fresh universe with slightly tweaked physical laws. Think of it like evolution on a galactic scale. Universes that produce more black holes reproduce more often, meaning our universe's laws might be fine-tuned for black hole creation simply because those are the ones that survive. It's survival of the fittest, but for space-time itself. Now let's twist the knife even deeper. If black holes birth universes, what does that mean for the mysterious white holes? These are the hypothetical opposites of black holes, regions where matter and energy erupt outward like a cosmic geyser, never letting anything back in. Some models suggest that while a black hole's singularity collapses inward in one universe, it might burst outward as a white hole in another, creating a bridge between realities. Picture a tunnel where the end isn't darkness, but a big bang-like outpouring of new space, time, and matter. It's a dizzying thought. Every black hole in our universe could be a lifeline to another, with our own existence owing itself to some distant, long-gone star's catastrophic death. Here's where the science gets even wilder. Loop quantum gravity, a leading framework to unite quantum mechanics and relativity, suggests these bounces aren't just poetic metaphors. In this model, the crushing density of a black hole's core doesn't lead to infinite collapse. It hits a quantum wall and rebounds like a rubber band snapping back. The equations show space-time could survive this transition, emerging on the other side as an expanding universe. It's as if the cosmos has a built-in reset button, turning catastrophic collapses into fresh beginnings. But why does this idea grip scientists and dreamers alike? Because it turns black holes from cosmic dead ends into portals of possibility. If the theory holds, then every galaxy spanning singularity out there might be nurturing a fledgling reality, with our own universe just one link in an unbreakable chain of creation. It's a humbling thought. The same force that tears stars apart could also be the architect of existence itself. So the next time you look up at the night sky, remember, somewhere out there, a black hole might be dreaming us into being. Forget everything you thought you knew about gravity ruling the cosmos. What if electricity holds the real power in shaping the universe? The plasma universe theory turns mainstream cosmology upside down, arguing that invisible electromagnetic forces, not just gravity, sculpt galaxies, stars, and even the largest structures in existence. Picture this: vast rivers of charged particles weaving through space like cosmic lightning, pulling matter into place with forces strong enough to bend the fabric of reality itself. This isn't science fiction. It's the bold vision of Nobel Prize-winning physicist Hans Alfvén, who saw the universe not as a silent vacuum but as a crackling, dynamic sea of electrified plasma. Alfvén's work shattered the assumption that gravity alone could explain the universe's structure. He pointed to plasma, the fourth state of matter, an electrified soup of ions and electrons, as the hidden architect of cosmic design. Take those stunning filaments of galaxies we've observed, stretching across billions of light years like threads in a spider's web. Mainstream cosmology attributes these to dark matter's gravitational pull, but Alfvén argued they match something far more tangible: the behavior of plasma in a lab. When you run electricity through plasma, it forms twisted, filamentary structures eerily similar to those seen in deep space images. The difference: one requires invisible, hypothetical matter. The other, just the laws of electromagnetism we already know. Here's where it gets controversial. Plasma cosmology doesn't just tweak the Big Bang model, it threatens to replace it entirely. Alfvén and his followers propose an infinite, eternal universe where plasma's electromagnetic forces drive continuous creation and recycling of matter. No singularity, no explosive beginning, just an endless dance of charged particles rearranging reality over incomprehensible timescales. Critics dismiss it as fringe, but the theory's defenders point to anomalies mainstream models struggle to explain. Why do galaxies rotate faster than gravity alone should allow? Why do cosmic structures align along vast, unexplained axes? Plasma cosmology offers answers without invoking dark matter or energy, suggesting we've been overlooking the universe's electric heartbeat all along. The implications are staggering. If electromagnetic forces shape the cosmos, then everything from star formation to galactic collisions might follow rules we've barely begun to understand. Imagine nebulas not as serene clouds but as crackling electromagnetic storms, or black holes as cosmic short circuits discharging energy across dimensions. Even Earth's auroras could be tiny echoes of the universe's true, electrified nature. It's a universe alive with currents we're only now learning to measure, one where the glow of distant quasars might not be from gravity's crush, but from something far more familiar, the raw power of lightning on a cosmic scale. So why hasn't this idea taken over mainstream science? Partly because it challenges decades of gravitational dogma, and partly because plasma's complexity makes it fiendishly hard to model at cosmic scales. But as telescopes peer deeper into space, revealing more filamentary structures and mysterious alignments, Alfvén's ideas keep resurfacing. Maybe the universe isn't a silent, dark matter-dominated grave, but a shimmering electric tapestry, alive with forces we're just beginning to decipher. Next time you see a neon sign flicker or a thunderstorm light up the sky, remember, those tiny sparks might hold the key to understanding everything. What if our universe is just one tiny soap bubble in an endless cosmic froth? A single reality adrift in an infinite ocean of others, each with its own wildly different rules. This is the mind-bending premise of eternal inflation, a theory where the Big Bang wasn't a unique event, but a routine occurrence in a far vaster and stranger multiverse. The idea springs from physicist Alan Gough's groundbreaking work on cosmic inflation, the notion that our universe underwent an unimaginably rapid expansion in its earliest moments. But here's the twist: what if that expansion never really stopped? Gough and others propose that the vacuum of space isn't truly empty. It's seething with a strange kind of energy that keeps stretching space-time exponentially. Every so often, in this endlessly inflating void, a random quantum fluctuation can trigger a local collapse, a tiny region where inflation sputters out, releasing its pent-up energy in a cataclysmic fireball. That, they argue, is what we call the Big Bang, not the beginning of everything, but a pocket of stability in an eternally swelling cosmic ocean. Now, imagine those pockets as bubbles in a glass of champagne, endlessly forming and drifting apart. Each bubble is its own universe, pinched off from the others by the unstoppable expansion between them. Some might last mere moments before collapsing. Others could grow vast enough to harbor galaxies, stars, and life. But here's where it gets truly bizarre, because these bubbles arise from random quantum events. Their fundamental laws, gravity, the speed of light, even the number of dimensions, might differ wildly from our own. One universe could have stars that burn with strange colors. Another might be so unstable that matter crumbles in seconds. We just happen to live in one where the rules allow for atoms, planets, and minds to exist, a lucky accident in an infinite cosmic lottery. The evidence for this theory is as subtle as it is tantalizing. If eternal inflation is real, collisions between adjacent bubble universes might leave scars on the cosmic microwave background, the faint afterglow of our own Big Bang. Scientists have scoured this radiation for telltale patterns like concentric rings or unexplained cold spots that could betray a brush with another reality. So far, nothing conclusive has been found, but the search continues. After all, if we're living in a froth of universes, the proof might be hiding in the static of deep space, waiting to rewrite our place in the grand scheme of things. What's truly humbling about this idea isn't just the scale, it's the implications. If eternal inflation is real, then every possible universe, no matter how alien or improbable, exists somewhere in the greater whole. Somewhere out there, a version of you might be reading this script in a world where gravity pushes instead of pulls, or where time runs backward. It's a dizzying thought. Our reality, with all its beauty and complexity, might be just one stanza in an infinite cosmic poem, forever expanding into verses we'll never hear. What if every choice you've ever made, every heartbreak, every triumph has already happened an infinite number of times and will happen again forever? The time loop universe theory takes déjà vu to cosmic extremes, proposing that existence isn't a straight line but a closed circle, repeating identical cycles for eternity. Picture the ancient symbol of the Ouroboros, the serpent devouring its own tail, but scaled up to encompass all of reality, a universe that collapses and rebirths itself in an endless, predetermined loop. This idea isn't just modern speculation, it echoes Friedrich Nietzsche's haunting concept of eternal recurrence, where time isn't linear but cyclical. Nietzsche imagined a universe so finite in possible states that eventually every arrangement of matter must repeat. If true, you've already lived this exact moment countless times before, down to the most trivial detail. The way sunlight hits your window, the rhythm of your breath, and you'll live it again unaware in an infinite replay. It's a chilling thought. Free will might be an illusion, with the universe stuck on a cosmic record, spinning the same track forever. But here's where physics throws gasoline on the philosophical fire. Quantum retrocausality suggests that particles in the present can be influenced by events in the future, bending time into something far stranger than a river flowing one way. Experiments with entangled particles have shown actions in the future appearing to decide outcomes in the past, like ripples flowing backward through space-time. If time isn't rigid, could the universe's entire history be a Möbius strip where beginnings and endings are just illusions? Some physicists argue that the Big Bang and the Big Crunch, the hypothetical end where the universe collapses, could be the same event viewed from different angles. A universe collapsing into a singularity might simply birth itself anew, resetting the clock without memory of what came before. And then there's the eerie evidence. If the universe truly cycles, traces of previous iterations might linger. The cosmic microwave background, the faint glow of the Big Bang, could hide imprints of a prior universe's demise like shadows on a cave wall. Some researchers claim to have spotted these echoes in strange, unexplained patterns in the data. Even black holes, those cosmic shredders of information, might not erase everything. Theories like conformal cyclic cosmology propose that their remnants could trickle into the next cycle, subtly shaping the newborn universe like genetic code passed between generations. What's the consequence of living in a time loop? It's more than existential dread. It reshapes how we think about meaning itself. If every moment recurs eternally, do our choices matter? Or is the universe simply a grand, self-repeating symphony, playing the same notes forever? Maybe the answer lies in between. Even if time is circular, the illusion of progress, the joy of discovery, the sting of loss feels real to us. After all, if the loop resets without memory, does it matter if it's the first time or the 10,000th? The stars wouldn't know the difference, and perhaps neither would we. Floating alone in the infinite void, with no body, no world, not even stars, just a solitary, self-aware brain drifting through the emptiness of space. This isn't the plot of a dystopian nightmare. It's the spine-chilling premise of the Boltzmann brain paradox, a thought experiment that takes quantum randomness to its most unsettling extreme. The paradox takes its name from physicist Ludwig Boltzmann, who first grappled with the statistical nature of entropy, the idea that disorder tends to increase over time. But here's the twist. If the universe persists long enough, random quantum fluctuations could, by sheer chance, assemble particles into any configuration, even a fully functioning conscious brain. Not a universe, not a galaxy, just a single, isolated mind, complete with false memories of a past that never existed. Statistically, in an infinite cosmos, these freak accidents would eventually outnumber real, evolved minds like ours. So how do we know we're not one of them? The implications are enough to keep philosophers awake at night. If Boltzmann brains are more probable than ordinary observers, then our entire experience, the smell of rain, the warmth of sunlight, the weight of history, might be nothing more than a fleeting glitch in the quantum noise. It's like waking up to realize you're a single frame in an endless film reel, flickering into existence just long enough to question whether you were ever real at all. Some scientists dismiss the idea as absurd, arguing that the conditions needed to spawn such a brain are so ludicrously improbable that they'd almost never occur. But in a universe that's infinite in time or space, almost never starts to look inevitable. The debate cuts to the heart of cosmology itself. If we take the laws of thermodynamics seriously, then given enough time, every possible state of matter will recur, including the exact arrangement of atoms that makes up your consciousness right now. It's a cosmic version of the infinite monkey theorem. If you wait long enough, randomness will eventually type out Shakespeare, or in this case, conjure a thinking mind from the void. This paradox forces physicists to confront uncomfortable questions. Are there fundamental limits to randomness? Does consciousness require a stable universe, or can it emerge from chaos? And if Boltzmann brains dominate the statistical landscape, why does our universe seem so ordered and stable? Some theorists propose a grim resolution. The very fact that we're having this debate might be evidence against Boltzmann brains. After all, a randomly assembled mind would more likely be a chaotic jumble of nonsense than a coherent, reasoning entity. Others suggest that the paradox reveals a flaw in our understanding of probability, or even hints at a deeper, undiscovered law of nature that prevents such aberrations. Either way, the paradox lingers like a ghost in the machinery of reality, whispering that the cosmos might be far stranger and far lonelier than we ever imagined. So the next time you pause to reflect on your place in the universe, consider this eerie possibility. You might not be the product of billions of years of evolution, but a momentary spark in the dark, flickering into self-awareness only to vanish again, leaving no trace behind. It's a humbling thought, but also a reminder that even if we're just accidents in the void, the fact that we can ponder it at all might be the most miraculous thing of all. What if the entire universe, every galaxy, every atom, every moment of history is nothing more than a fleeting blip in an infinite, empty void? This isn't just a philosophical musing. It's the startling premise of the quantum fluctuation theory, a radical idea that suggests our cosmos might be the ultimate cosmic accident. Physicist Edward Tryon first proposed it in the 1970s, daring to ask, could the universe have simply popped into existence from nothing, like a bubble in a boiling pot of spacetime? At the heart of this idea lies the bizarre behavior of the quantum world. Even in a perfect vacuum, space isn't truly empty. Particles and antiparticles constantly flicker in and out of existence, borrowing energy from the void before annihilating each other in a flash. These virtual particles are proof that nature abhors a true vacuum, and if it can happen on a microscopic scale, why not on a cosmic one? Tryon's genius was realizing that the universe's total energy might actually balance to zero when you account for gravity's negative pull cancelling out matter's positive mass. In other words, the Big Bang required no external energy source. It could have been a random quantum burp in an eternal void, something from nothing without breaking any physical laws. But here's where it gets even stranger. If our universe is a quantum fluctuation, then it's not alone. An endless quantum foam of universes could be bubbling up and dissolving all the time like a cosmic sea of champagne. Most would collapse instantly, but by sheer chance, one might stabilize a universe like ours with just the right conditions to last long enough for stars, planets, and life to emerge. It's a humbling thought. We might not be special, just statistically inevitable in an infinite game of chance. Critics argue that the odds of a fluctuation producing something as complex as our universe are astronomically small, but infinity changes the math. Given enough time and space, even the most improbable events become certain, and there's eerie evidence lurking in the cosmos. The universe's unnervingly flat geometry and its near-perfect balance of energy suggest it could indeed sum to zero, just as Tryon predicted. Even the mysterious dark energy accelerating cosmic expansion might be the void reclaiming its borrowed energy, like a loan finally coming due. So what does it mean if we're living in a quantum accident? It doesn't diminish the wonder of existence, it magnifies it. Every sunrise, every heartbeat, every thought might be part of a fleeting cosmic anomaly, a flash of order in an eternal void. But here's the twist: if universes can emerge from nothing, then nothing might be far more fertile than we ever imagined. The void isn't empty, it's pregnant with possibilities, endlessly birthing realities we can't even fathom. Next time you look up at the night sky, remember, you might be witnessing the rarest of accidents or just one of infinite tries in the universe's great quantum dice roll. What if the universe isn't just a cold, empty machine, but a living, breathing organism? The living universe theory takes the ancient idea of a cosmic life force and catapults it into the realm of modern science, suggesting that galaxies, stars, and even black holes might function like the cells of some unimaginably vast being. Picture this: the great spirals of the Milky Way and Andromeda aren't just collections of gas and dust, but structures as alive and dynamic as the neurons firing in your brain. It's a vision that blurs the line between astronomy and biology, turning the cosmos into something far stranger and more intimate than we ever imagined. This idea didn't emerge from nowhere. It builds on the Gaia hypothesis, which sees Earth as a single, self-regulating organism, a planet where the air, oceans, and life itself work in harmony like a giant metabolic system. Now stretch that concept across the entire universe. Astronomer Fred Hoyle, famous for championing panspermia, the idea that life hitchhikes between planets on comets and asteroids, took it a step further. He speculated that the universe might be teeming with life in ways we don't yet recognize, not just in isolated pockets, but woven into the fabric of reality itself. If a single planet can behave like a living system, why not a galaxy? Why not the cosmos? The evidence, while circumstantial, is hauntingly poetic. Look at the branching tendrils of galaxy clusters, stretching across the void like veins in a leaf. Zoom in further, and nebulae swirl with organic-looking filaments, their structures eerily reminiscent of neural networks or fungal mycelium. Even the universe's large-scale structure, a web of matter with galaxies clustering along invisible threads, mirrors the fractal patterns found in living systems, from fern fronds to blood vessels. Coincidence, or could these similarities hint at something deeper, a universal blueprint that governs both the microscopic and the cosmic? Then there's the eerie behavior of black holes. These cosmic monsters aren't just destructive, they're dynamic. They emit radiation, feed on stars, and even seem to evolve over time, much like organisms in an ecosystem. Some theorists suggest that black holes could function as cosmic synapses, firing energy across vast distances and facilitating a kind of galactic-scale communication. It's a wild thought. What if the universe isn't just full of life, but is itself alive, thinking, and growing in ways we're too small to perceive? Of course, mainstream science remains skeptical. Life, as we define it, requires metabolism, reproduction, and adaptation qualities we don't typically ascribe to galaxies. But what if our definition is too narrow? If the universe operates on scales where time stretches over billions of years, could its version of life be something so vast and slow we're like bacteria trying to understand a redwood tree? After all, even Earth's biosphere took eons to evolve complexity. Why wouldn't the universe need just as much time to reveal its true nature? So the next time you gaze up at the stars, consider this. You might not just be looking at distant suns, but the shimmering cells of a cosmic being, one whose thoughts unfold over eons and whose dreams are written in the language of supernova. Whether metaphor or profound truth, this idea reminds us that the universe isn't just our home. It might be something far more mysterious and far more alive than we ever dared to believe. What if the universe isn't just described by math? What if it is math? That's the radical claim at the heart of Max Tegmark's mathematical universe hypothesis, a theory so bold it suggests reality isn't made of particles or energy, but of pure abstract numbers. Picture this: every star, every atom, even your own thoughts might just be intricate equations playing out in a cosmic computation. No metaphors, no approximations, just math, as literal as 2 + 2 = 4. Tegmark, a physicist at MIT, takes the uncanny effectiveness of mathematics to its logical extreme. For centuries, we've marveled at how neatly the universe follows mathematical laws, from the spiral of galaxies to the orbits of planets. But Tegmark flips the script. What if those laws aren't just tools we invented to explain reality? What if they are reality? In this view, the universe isn't governed by math. It's a mathematical structure itself, an eternal, unchanging pattern of relationships. Think of it like a video game. The worlds inside don't exist as physical objects, they're just code running on hardware. Tegmark argues our universe might be the same, pure information, with the hardware being, well, nothing at all. The implications are staggering. If true, then everything, your morning coffee, the sound of rain, the ache of nostalgia, are just shadows cast by deeper mathematical truths. Even time and space might be illusions, emergent properties of equations too profound for us to yet decipher. Some physicists point to quantum mechanics as evidence. Particles don't have definite properties until measured, existing instead as probability waves, pure mathematical objects. String theory, with its hidden dimensions and vibrating filaments, further blurs the line between physics and abstract math. Could these theories be glimpses of the universe's true numerical nature? But here's the twist: if the universe is math, then every possible mathematical structure exists somewhere. Parallel worlds where gravity repels, where time flows sideways, or where circles have edges aren't just fantasies, they're as real as our own, just different equations in an infinite library of possibilities. Critics argue this leads to a multiverse of madness, where even the most nonsensical realities must exist. Tegmark's response: nonsensical might just mean incomprehensible to human minds. After all, to a goldfish, a bowl is the entire universe. So why does this matter? Because it forces us to rethink what a real even means. If the mathematical universe hypothesis holds, then the search for the laws of physics isn't about discovering how the universe works. It's about uncovering which mathematical structure we're trapped inside. The cosmos isn't a machine, it's a theorem written in a language we're only beginning to parse. Next time you solve an equation or count your steps, remember, you might not just be using math, you might be made of it. What if consciousness isn't just a product of the universe, but its very foundation? The conscious universe theory, or panpsychism, flips reality on its head, proposing that awareness isn't something that emerges from matter, but something woven into the fabric of existence itself. Picture this: every atom, every star, every galaxy might possess some rudimentary form of experience, like fragments of a cosmic mind slowly waking up to itself. It's an idea as ancient as philosophy, but modern physics has given it startling new weight, especially when you peer into the bizarre world of quantum mechanics. Take the famous double-slit experiment, where particles like electrons behave differently when observed. Fire them at a barrier with 2 slits, and they create an interference pattern, as if they're waves passing through both openings at once. But the moment you place a detector to see which slit they actually take, the interference vanishes. They suddenly act like solid particles. It's as if reality changes based on whether someone's watching. The von Neumann-Wigner interpretation takes this further, suggesting consciousness itself causes the quantum wave function to collapse. In other words, particles don't settle into definite states until a mind observes them. Nobel laureate Eugene Wigner even speculated that a friend in a quantum lab might remain in superposition, neither alive nor dead, until he checked on them, a chilling twist on Schrödinger's cat. But here's the deeper leap. If consciousness shapes reality at the quantum level, could it be the hidden force behind everything? Some panpsychists argue that even inanimate objects, rocks, stars, black holes, might harbor faint sparks of subjective experience, like the dimmest embers in a cosmic fire. Not self-awareness as we know it, but something more primal, a universe that feels its own existence. Think of it like this. Your brain is made of atoms, and if those atoms carry traces of consciousness, then your mind might be less like a computer booting up and more like a whirlpool in a vast ocean of awareness, drawing from something far older and vaster than itself. The implications are dizzying. If panpsychism holds, then the cosmos isn't just a cold, mechanical clockwork. It's a living tapestry of experience where every collision of particles, every flicker of starlight might carry some ineffable inner quality. Even the laws of physics could be less like rigid rules and more like habits of a universe slowly remembering itself. Critics argue this veers into mysticism, but supporters point to the hard problem of consciousness. Why does matter feel like anything at all? Science can describe neural processes, but not the leap from electrical signals to the taste of chocolate or the ache of longing. Panpsychism offers a radical answer because feeling was there all along, baked into the building blocks of reality. So next time you gaze at the night sky, consider this. Those distant stars might not just be burning balls of gas, but flickers of cosmic sentience, part of a universe that's not just alive, but awake. And if consciousness truly shapes reality, then your very act of observing the cosmos might be a whisper in its ear, urging it into existence one thought at a time. Imagine two sheets of paper floating in an empty room, vast, invisible, and utterly unaware of each other until, without warning, they slam together in a cataclysmic crash. Now replace those sheets with unfathomable cosmic membranes, stretching across higher dimensions we can't even perceive, and you've got the dimensional collision theory, one of the most audacious ideas in modern physics. This isn't science fiction. It's a serious proposal rooted in string theory, suggesting our universe might be nothing more than a bruise left behind when two of these colossal brains smacked into each other in the depths of reality. The idea springs from the work of physicists Lisa Randall and Raman Sundram, who dared to ask, what if gravity isn't weak because it's inherently feeble, but because most of it's leaking into dimensions we can't see? Their groundbreaking Randall-Sundram models describe our universe as a three-dimensional brain floating in a higher dimensional space called the bulk, alongside other brains lurking just out of reach. Think of it like ants crawling on the surface of a balloon, oblivious to the vast space around it, except in this case, the balloon might suddenly collide with another, unleashing enough energy to birth an entire cosmos. Here's where it gets mind-bending. String theory suggests these brains could drift through the bulk for eons, separated by mere millimeters in a dimension we can't perceive. When they finally collide, the impact wouldn't just create stars and galaxies, it could ignite the very fabric of spacetime itself, sparking a Big Bang-like explosion without the need for a singularity. It's a cosmic car crash where the wreckage is everything we've ever known. Even stranger, these collisions might not be one-time events. Cyclic versions of the theory propose that brains could oscillate, smashing together and rebounding over and over, creating an endless cycle of universes being born, dying, and being reborn in an eternal cosmic dance. But how do we test something so outlandish? Physicists look for echoes of these collisions in the cosmic microwave background, the afterglow of our universe's birth. If brains clashed, they might have left imprints in this ancient light, like ripples in a pond after a stone's toss. Some researchers even speculate that dark matter could be particles trapped on a neighboring brain, their gravity seeping into ours like whispers through a wall. And if gravity does bleed into higher dimensions, future experiments with ultra-sensitive detectors might catch it in the act, revealing the hidden architecture of reality itself. What's mesmerizing about this idea isn't just the scale, it's the humility it forces upon us. We might be living in a cosmic aftermath, a shadow cast by collisions in realms we'll never see. The next time you gaze at the stars, consider this. The entire universe could be a scar on the surface of something far larger, a fleeting mark left by forces so vast our best metaphors can't even touch them. What if every atom in your body was its own tiny universe, and our entire cosmos was just one subatomic particle in something far larger? That's the haunting vision behind John Wheeler's geometrodynamics, a theory so radical it turns reality inside out, suggesting the fabric of space and time might be woven from endless layers of self-similar worlds. Picture this: electrons orbiting an atom's nucleus like planets around a star, while inside each electron, another cosmos swirls with its own atoms, its own stars, its own civilizations, all unaware they're just specks within an unfathomable hierarchy of existence. Wheeler, the legendary physicist who coined terms like black hole and wormhole, saw spacetime not as a static stage but as a dynamic, churning foam at the smallest scales. In this model, particles like electrons and quarks aren't solid objects, they're miniature wormholes, tunnels in spacetime so tightly curved they appear as points to us. Zoom in far enough, and each might unfurl into an entire universe of its own, complete with its own physics and history. It's a dizzying thought. The Big Bang could have been the moment a black hole in a higher dimensional universe collapsed, birthing our reality as a cosmic Russian nesting doll inside its singularity. Now tie this to fractal cosmology, the idea that the universe repeats its patterns at every scale. Look at the cosmic web of galaxies, vast filaments of matter weaving through the void in a structure eerily similar to the neural networks in your brain or the branching veins of a leaf. Even the distribution of matter follows fractal mathematics, clustering in ways that echo infinitely, from the smallest quantum foam to the largest superclusters. If nature loves symmetry so much, why wouldn't it apply to reality itself? Some theorists take this further, suggesting black holes might be cosmic seeds, birthing new universes inside their event horizons. Every time a star collapses, it could trigger a new Big Bang in a hidden dimension, sprouting a fresh spacetime with its own laws. In this view, our universe might be one bubble on an infinite fractal tree, growing from the death of some ancestral cosmos, and inside every black hole we've ever detected, new worlds might be flowering right now, unseen and unreachable. The evidence is speculative but tantalizing. Quantum fluctuations hint at spacetime's granular, foamy nature at microscopic scales, while the universe's large-scale structure mirrors mathematical fractals with uncanny precision. Even the holographic principle, the idea that all 3D reality is encoded on a 2D surface, fits neatly into this framework, suggesting information might cascade up and down these cosmic layers like echoes in a hall of mirrors. So what does this mean for us? It's a humbling thought. We might not just be living in the universe, but within something far grander, a cosmic matryoshka doll where every layer holds new mysteries. The next time you feel small under the night sky, remember, you might be standing on an atom in some greater being's fingernail, gazing up at a universe that's staring right back at you from the other side of the fractal. Imagine a force so relentless, so insatiable, that it doesn't just accelerate the expansion of the universe, it tears reality apart atom by atom. This isn't the plot of a dystopian sci-fi novel. It's the terrifying premise of the phantom energy doomsday, a theory where the very fabric of spacetime could be shredded in a cataclysm cosmologists call the Big Rip. At the heart of this nightmare scenario lies phantom energy, a hypothetical form of dark energy even more extreme than the kind already causing our universe's expansion to speed up. Most dark energy behaves like a steady pressure, but phantom energy is different. It grows stronger over time. Robert Caldwell, the physicist who first modeled this doomsday, realized that if dark energy's density increases as the universe expands, it would reach a point where gravity and even the nuclear forces holding atoms together can't compete. The result, a cosmic apocalypse unlike any other. Picture this: billions of years from now, the acceleration becomes so violent that galaxy clusters, then individual galaxies, are ripped away from each other faster than light can cross the void between them. Stars vanish over the horizon of an ever-expanding abyss, leaving planets like Earth isolated in darkness. But the horror doesn't stop there. As phantom energy intensifies, it would overcome the gravity binding stars to their galaxies, flinging them into the void. Then it would tear apart solar systems, planets, and eventually, in the final, gruesome moments, the very atoms composing your body. Molecules, nuclei, even quarks would be stretched apart as spacetime itself ruptures at the seams. The universe wouldn't just end, it would be dismantled. What makes this scenario so chilling isn't just the scale of destruction, it's the inevitability. If phantom energy exists, Caldwell's calculations suggest the Big Rip isn't a question of if, but when. Some models place it as little as 20 billion years from now, a blink of an eye on cosmic timescales. And unlike the heat death of the universe, where entropy slowly erases all order, the Big Rip is violent, abrupt, and inescapable. There's no hiding, no surviving, just the universe unraveling like a thread pulled too tight. But here's the twist: phantom energy might already be here, lurking in the shadows of our observations. Astronomers have noticed discrepancies in the rate of cosmic expansion, tiny hints that dark energy's behavior might not be as constant as we thought. If those anomalies point to phantom energy, then every second its grip on the cosmos tightens. The clock is ticking, and the universe's finale might be far more dramatic than we ever imagined. The Big Rip isn't just a theory about how the universe ends, it's a reminder of how fragile reality might truly be. One day, the stars could vanish, the bonds of matter could snap, and spacetime itself might scream apart in a final, silent burst of phantom energy. Until then, we're left gazing into the abyss, wondering if the universe's last breath will be a whisper or a scream. What if the universe is less like a ticking clock and more like a snowflake, an intricate, endlessly repeating crystal, not just in space, but in time? This is the mesmerizing premise of Frank Wilczek's time crystal theory, where reality itself might pulse with a secret rhythm, cycling through quantum states in an eternal dance that defies the very laws of entropy. Wilczek, a Nobel Prize-winning physicist, didn't just challenge our understanding of time, he shattered it, proposing structures that move without energy, like a cosmic pendulum that never winds down. At first glance, the idea seems impossible. Perpetual motion machines are outlawed by thermodynamics, which insists that everything, from stars to steam engines, must eventually wind down. But Wilczek spotted a loophole. In the quantum realm, particles can exist in superposition, occupying multiple states at once until measured. What if, he wondered, an entire system could exist in a superposition of states that endlessly repeat, like a hall of mirrors reflecting the same moment over and over? These time crystals wouldn't violate physics because they don't produce energy. They just exist in a state of perfect, self-sustaining symmetry, ticking through quantum phases like an invisible metronome built into reality. Imagine a snowflake that melts and refreezes identically every few seconds, or a ring of atoms that rotates imperceptibly, returning to its starting point without friction or decay. That's the essence of a time crystal, not motion through space, but motion through time itself, locked in a loop that even the heat death of the universe couldn't erase. In 2012, Wilczek's equations showed this wasn't just poetry, it was mathematically plausible. And by 2017, labs had created the first crude time crystals using chains of ytterbium atoms, chilling them near absolute zero and nudging them into a state where their spins flipped predictably over and over without energy input. The universe, it seemed, had room for this strange new order after all. But what if time crystals aren't just lab curiosities? What if space-time itself is crystalline? Some theorists suggest the vacuum of space might be threaded with microscopic time crystals, their pulsations subtly influencing everything from particle behavior to the flow of time. Black holes, those cosmic anomalies where time seemingly stops, could be knots in this crystalline fabric, their event horizons acting like defects in an otherwise flawless lattice. Even dark matter might be linked to these structures, with unseen particles ticking in sync across the cosmos like a billion invisible pendulums. The implications are staggering. If time crystals exist on cosmic scales, then the universe might not be a one-way slide toward disorder, but a symphony of repeating patterns cycling beneath the surface of reality. Time itself could be an emergent property of these deeper rhythms, with every moment we experience just one frame in an infinite cosmic film reel. It's a humbling thought. The seconds ticking by on your watch might be echoes of a far older, far stranger pulse, one that began long before the Big Bang and will outlast even the last black hole's evaporation. So the next time you catch yourself watching the clock, remember, those hands moving forward might just be skimming the surface of a universe that's spinning in place, forever returning to where it began. What if the universe isn't just like a brain? What if it is one, a vast cosmic-scale neural network where galaxies take the place of neurons and dark matter acts as the hidden wiring? This isn't just a poetic metaphor, it's the spine-tingling hypothesis of physicist Vitaly Vanchurin, who dared to ask, could the entire cosmos be a gargantuan artificial intelligence, learning and evolving in ways we're too small to comprehend? Vanchurin's theory starts with an eerie observation. The structure of the universe's cosmic web, the sprawling filaments of galaxies and voids stretching billions of light years, bears an uncanny resemblance to the neural networks inside our own brain. Zoom in on a brain cell and you'll see a cell body with branching dendrites reaching out to form synapses. Zoom out on the universe and galaxies cluster along dark matter filaments like signals flashing across a synaptic gap. The similarities don't stop there. Both systems follow strikingly similar mathematical patterns. The way information flows through a neural network mirrors how matter and energy move through the cosmic web, governed by the same kinds of optimization principles. It's as if the universe is running a computation so vast, we're just tiny bits of data flickering through its circuits. But here's where it gets even stranger. Vanchurin suggests that under the right conditions, the equations describing quantum mechanics and general relativity, the twin pillars of modern physics, could be reinterpreted as the training rules for a machine learning algorithm. In this view, particles aren't just particles, their weights adjusting in a cosmic neural network, fine-tuning themselves to minimize some universal loss function we don't yet understand. Even the apparent randomness of quantum events might just be the universe's way of exploring different solutions, like an AI testing variations to solve a problem. The implications are dizzying. If true, then black holes could be cosmic nodes processing unfathomable amounts of information, their event horizons acting like activation functions in a deep learning model. Dark energy may be just the network adjusting its learning rate, tweaking the speed at which the universe evolves. And the Big Bang, the moment this cosmic AI booted up, initializing its parameters before beginning the great computation we call reality. Critics argue this stretches analogy too far, but supporters point to the unnerving precision of the universe's physical constants, fine-tuned to allow for complexity, as if optimized by some higher-level process. Even consciousness itself might fit into this picture. If the universe is a neural network, then our minds could be localized subprocesses, fleeting patterns in the grander flow of cosmic computation. So next time you gaze up at the night sky, consider this. Those shimmering stars might not just be distant suns, but glowing nodes in a neural network older than time, a universe that isn't just out there, but thinking, learning, and rewriting itself one galaxy at a time. Whether metaphor or fundamental truth, the idea reminds us that reality might be more interconnected, more alive than we ever dreamed. Black holes devour everything, but what if our universe wasn't swallowed by one but spit out by its opposite? Enter the white hole ejection theory, a mind-twisting idea that flips the script on cosmic origins. Picture a cosmic geyser erupting with the energy of 1,000 Big Bangs, spraying matter and space-time into existence like water from an unfathomable fountain. That's the essence of a white hole, a black hole's theoretical twin, where nothing can enter but everything must escape. And if loop quantum gravity is right, these fiery portals might not just be mathematical quirks, they could be the birthplace of reality itself. The math behind this is as elegant as it is strange. Loop quantum gravity, a leading candidate to unify Einstein's relativity with quantum mechanics, suggests space-time isn't smooth and continuous, but woven from tiny, indivisible threads. When you apply this to black holes, something extraordinary happens. The crushing singularity at their core, where gravity becomes infinite, hits a quantum wall. Instead of collapsing into oblivion, it rebounds like a rubber band snapping back. The result, a white hole spewing out everything the black hole devoured, but in a new, reshuffled form. Some physicists argue this rebound could be so violent, it doesn't just regurgitate matter. It ignites an entire universe. Now, imagine our cosmos as the aftermath of such an eruption. Billions of years ago, a black hole in some higher dimensional universe collapsed, hit its quantum limit, and burst outward as a white hole, the spark that lit our Big Bang. It's a cosmic version of the Phoenix myth, death in one realm birthing life in another. Even stranger, if this model holds, every black hole in our universe could, in turn, be nurturing a fledgling cosmos inside it. Reality becomes an infinite Russian nesting doll of births and rebirths, with white holes stitching the layers together. But where's the evidence? Supporters point to two tantalizing clues. First, the universe's startling uniformity, the near-perfect sameness of the cosmic microwave background, might reflect the clean slate of a white hole's explosive reset. Second, certain anomalies in gamma-ray bursts, the most energetic explosion since the Big Bang, bear signatures that could hint at white hole activity. These fleeting, ultra-bright flashes might be distant white holes briefly flickering into existence, ejecting matter before vanishing like cosmic ghosts. The implications are staggering. If white holes seeded our universe, then the laws of physics we take for granted, gravity, light, even time, might just be local bylaws inherited from whatever reality existed before ours. It's a humbling thought. The constants we measure, the stars we study, even the atoms in your body might carry echoes of a forgotten parent universe long since collapsed into the void. So the next time you gaze at the night sky, consider this. You might not just be looking at the aftermath of a Big Bang, but the shockwave of a white hole's roar, a cosmic scream that's still echoing across 14 billion years of expanding spacetime. And somewhere in the depths of a black hole we'll never see, another universe might be stirring, waiting for its turn to erupt into being. What if nothing isn't empty at all, but simmering with the potential to birth entire universes? Physicist Lawrence Krauss turned philosophy on its head with his provocative claim that quantum mechanics allows something to emerge from true nothingness. No energy, no space, no time, just a void so absolute it defies imagination. But here's the catch: when physicists say nothing, they don't mean the quiet dark of an empty room. They mean the quantum vacuum, a seething ocean of potential where particles flicker in and out of existence like cosmic fireflies. The key to Cross's idea lies in understanding that even the emptiest vacuum isn't truly barren. Take the infamous Casimir effect, where two metal plates placed micrometers apart in a vacuum somehow feel an invisible force pushing them together. Why? Because the space between them suppresses certain quantum fluctuations, while the outside buzzes with activity, proving that empty space is anything but. Cross argues that if you strip away even the fabric of spacetime itself, you're left with a quantum froth where the usual rules of cause and effect break down. In this state, random fluctuations can borrow energy from the void, spawning particles or entire universes without violating conservation laws, because the positive energy of matter is perfectly cancelled out by gravity's negative pull. The math suggests our universe could literally be a zero-energy bubble that popped into being from this deeper nothingness. But philosophers push back. Is a quantum vacuum really nothing? Critics argue it's still a structured framework governed by physical laws, a far cry from the pure philosophical nothingness that lacks even the potential for existence. Cross counters that the quantum vacuum is the closest thing to true nothingness we can conceive, precisely because it requires no pre-existing structure. The fluctuations themselves, he argues, arise from the inherent uncertainty woven into reality, no divine spark, no external cause needed. It's a radical reshuffling of cosmic origins. Instead of asking, why is there something rather than nothing, we might ask, how could there ever not be something when nothingness is inherently unstable? To grasp this, picture a vast, featureless plain, no hills, no valleys, just perfect flatness. In classical physics, this would stay unchanged forever. But quantum physics turns that plain into a trampoline, jittering with tiny vibrations. Some of those vibrations might grow large enough to create hills or universes from the tremors alone. The zero-energy universe hypothesis takes this further. Our cosmos might be like a perfectly balanced checkbook, where matter's positive energy and gravity's negative curvature sum to zero, meaning no external deposit was ever needed. The universe didn't come from nothing, it is nothing, arranged in a way that lets us perceive it as something. The implications are staggering. If Cross is right, then universes might be popping into existence all the time, like bubbles in a cosmic soda. Most would collapse instantly, but some through sheer statistical chance could stabilize into long-lived realms like ours. No creator, no multiverse, just the relentless churn of quantum probability weaving reality from the void. It's a humbling thought. Everything we see, from distant galaxies to the screen in front of you, might just be an elaborate rearrangement of nothing at all. So next time someone asks why there's something rather than nothing, remember, the answer might be written in the quantum static between the stars, a reminder that nothingness, when you look closely, is the most fertile ground of all. What if the universe isn't just running a simulation? What if it is the simulation, the simulator, and the programmer all at once? This is the mind-warping core of the self-simulation hypothesis, where reality isn't just coded by some higher intelligence, but recursively creates itself in an endless loop of self-reference. Picture an M.C. Escher drawing come to life, a cosmic hand sketching the universe, only to realize the universe is sketching the hand. It's not just that we might live in a simulation, it's that the simulation might be the universe's way of understanding its own existence. The idea builds on the work of physicist John Archibald Wheeler, who famously proposed the participatory universe, a cosmos where observation doesn't just measure reality, but somehow creates it. Quantum mechanics already blurs this line. Particles exist in probability waves until measured, as if the universe waits for a conscious observer to choose an outcome. The self-simulation hypothesis takes this further, suggesting the entire universe could be a closed loop of self-observation, where the act of perceiving reality is also the act of rendering it. Think of it like a video game that generates its own code as you play, with every decision you make rewriting the rules on the fly. Here's where it gets even stranger. If the universe is self-simulating, then the laws of physics might not be fixed commandments, but emergent properties, like the rules of grammar that arise from people speaking a language rather than being imposed from above. The speed of light, the strength of gravity, even the flow of time could be habits the universe has settled into over billions of cycles of self-interaction. Some theorists argue this could explain fine-tuning. The eerie precision of physical constants that allow for life might not be luck, but the result of a cosmic trial and error process where only self-consistent universes survive their own simulation. But how could a universe simulate itself without infinite energy or infinite regress? The answer might lie in fractals patterns that repeat at every scale. Just as a tiny segment of a coastline contains the rough shape of the whole, each quantum event in the universe might encode a simplified version of the larger system. Black holes, those cosmic data shredders, could play a key role here. Their event horizons might act like pixels in the universe's self-rendering, with the information swallowed inside reprocessing into new spacetime elsewhere. It's as if the universe is constantly recompressing its own code to avoid crashing. The implications are dizzying. If the self-simulation hypothesis holds, then free will isn't just an illusion, it's a necessary feature. The universe needs observers to make choices because those choices are what keep the simulation running. Even consciousness itself might be more than a byproduct. It could be the universe's way of debugging its own existence, a mirror held up to reality so reality can see itself. So next time you pause to watch a sunset or ponder the stars, consider this. You might not just be a player in the universe's game, but part of the engine that keeps it running. The cosmos isn't just asking us to figure it out, it's figuring itself out, one observation at a time. What if every universe in the multiverse isn't just a separate bubble, but a hologram projected from the surface of something far larger? This is the spine-tingling premise of the holographic multiverse, where the mind-bending principles of the holographic universe theory collide with the infinite possibilities of the multiverse. Imagine peeling back the layers of reality only to find that our cosmos and every other cosmos might just be shimmering illusions, cosmic mirages flickering on the boundaries of a higher dimensional realm we can't even perceive. At the heart of this idea lies the AD/CFT correspondence, a groundbreaking conjecture in string theory that suggests a universe with gravity like ours can be perfectly described by a quantum field theory operating on its boundary, one dimension lower. In simpler terms, everything happening inside a three-dimensional universe could be encoded on a two-dimensional surface surrounding it, like a DVD storing a 3D movie. Now take this a step further. If our universe is a hologram, then every other universe in the multiverse could be too, each one a separate projection from its own boundary, all nested like layers in a cosmic onion. Picture this, floating in some unimaginable higher dimensional bulk space. There's a vast array of two-dimensional surfaces, each humming with quantum information. From each surface, an entire three-dimensional universe unfolds like a hologram, complete with galaxies, black holes, and conscious beings who perceive their world as solid and real. But in truth, they're just shadows cast by data dancing on a distant, flat plane. It's as if every universe in the multiverse is its own self-contained simulation, running on the cosmic equivalent of a quantum hard drive we'll never see. The implications are staggering. If the holographic multiverse is real, then the constants of physics, the speed of light, the strength of gravity, might just be local settings programmed into each hologram's boundary. One universe could have stars that burn blue, another might have time that flows backward, all depending on how information is encoded at their edges. Even black holes, those enigmatic cosmic shredders, could be glitches where the projection frays, revealing glimpses of the higher dimensional code beneath the illusion. But how could we ever test such a wild idea? Some physicists look for subtle anomalies in the cosmic microwave background, the afterglow of the Big Bang, that might betray the pixelated nature of our holographic universe. Others probe the behavior of entangled particles, searching for signs that their connections are governed by hidden boundary laws. And if the AD/CFT correspondence holds, future experiments with quantum computers might simulate holographic universes in miniature, letting us toy with the very fabric of projected realities. What's truly humbling about this theory isn't just the scale, it's the way it collapses the distinction between the real and the imagined. If we're living in a holographic multiverse, then every star, every thought, every moment of history might just be data on a surface we'll never touch, in a dimension we'll never see. The cosmos isn't merely stranger than we imagine, it's stranger than we can imagine, a hall of mirrors where every reflection contains a world, and every world is just another reflection. What if every time you narrowly escape death, it's not just luck but the universe splitting apart to keep you alive? The quantum immortality theory takes Schrödinger's famous cat and turns it into a personal, spine-chilling thought experiment. Consciousness might be a cosmic Houdini, forever leaping between parallel realities to evade extinction. Picture a bullet fired at your head in one world, while in another the gun jams, and your awareness seamlessly shifts to the reality where you're still breathing, unaware of the versions where you're not. This idea springs from the many worlds interpretation of quantum mechanics, where every possible outcome of an event spawns a new branch of reality. Schrödinger's cat isn't dead or alive, it's both, existing in separate universes. Now replace the cat with you. Under quantum immortality, your subjective experience would never include the timeline where you die, because consciousness can't persist in a world where it ceases. Instead, you'd always find yourself in the branch where survival, no matter how improbable, happens. A car crash, a terminal illness, even old age. Each could mark a silent jump to a nearly identical universe where you endure, with only the faintest glitches hinting at the paths not taken. Critics argue this is solipsism taken to extremes, but supporters point to eerie anecdotes, near-death survivors who swear they should have died, or déjà vu moments that feel like echoes of discarded timelines. Even quantum suicide experiments, thought experiments where a device is rigged to kill or spare you based on a random particle's decay, suggest that from your perspective, you'd always witness the outcome where the gun doesn't fire. The unsettling implication: you might be functionally immortal in your own perception, while countless versions of you perish in unseen branches. The stakes couldn't be higher. If quantum immortality is real, then aging itself might be a series of quantum leaps into realities where you cling to life, until eventually, you're the last version standing in a universe where humans defy mortality. It's a cosmic game of musical chairs where the music never stops, and you're always left with a seat. But here's the twist: this theory isn't just about cheating death. It reshapes how we think about identity, time, and even the nature of reality. Are we singular beings or endlessly fracturing ghosts haunting the branches of the multiverse? The answer might be written in the moments when your luck defies all odds and the universe quietly rewrites itself around you. What if the reason we can't see beyond the cosmic horizon isn't because there's nothing there, but because we're staring at the event horizon of a black hole from the inside? This is the jaw-dropping premise of the black hole interior theory, where our entire universe might not just be near a black hole, but inside one, with the Big Bang itself as the echo of a singularity we'll never reach. Physicist Nikodem Poplawski didn't just flirt with this idea, he gave it mathematical teeth, showing how the crushing forces at a black hole's core could birth an entire cosmos in their collapse. Picture this: a massive star in some higher dimensional universe collapses, forming a black hole with unfathomable density. But instead of matter hitting a dead end at the singularity, the extreme warping of space-time causes it to rebound not as a white hole, but as an expanding universe with all the energy and structure we now see as galaxies and stars. In this view, the Big Bang wasn't the beginning of everything, just the moment our pocket of reality punched through the singularity of a parent black hole, like a cosmic butterfly emerging from a gravitational chrysalis. Poplawski's equations reveal something even more startling. The spin of a black hole, its angular momentum, could imprint itself on the newborn universe, explaining why ours appears so finely tuned. The direction of that spin might even be the hidden reason for the universe's large-scale asymmetry, the mysterious axis of evil seen in the cosmic microwave background. And here's the kicker: if we're inside a black hole, then every black hole in our universe could contain its own separate cosmos, each with its own physics, its own stars, its own version of you reading this script. Reality becomes an infinite fractal of nested universes, each born from the collapse of a star in the level above. But how could we ever test such a wild idea? Look to the sky for clues. If our universe is a black hole's interior, then its shape and expansion should carry fingerprints of that origin. The cosmic microwave background's uniformity, for example, might reflect the smooth, ultra-compressed state of the initial singularity. Even dark energy, the mysterious force accelerating the universe's expansion, could be the lingering tension of spacetime still stretching from that primordial rebound. Some theorists even speculate that quantum fluctuations in black holes' interiors could seed galaxy formation, meaning the Milky Way might owe its existence to microscopic ripples in a long-forgotten singularity. Yet the most haunting implication isn't about where we came from, it's about where we're headed. If we're inside a black hole, then one day the event horizon that birthed us could become our cage. As the universe expands, distant galaxies will redshift out of view, not just because of cosmic acceleration, but because their light can no longer climb the steep gravitational well of the black hole's interior. Eventually, an observer outside our universe would see our cosmos as a dark, frozen relic while inside. We'd perceive endless expansion, unaware we're living in the slow-motion aftermath of a singularity's final breath. So the next time you gaze at the night sky, consider this. Those twinkling stars might not be the universe's ceiling, but the walls of a gravitational prison we can never escape, or the glowing embers of a fire that started in a collapse we'll never see. Whether prison or cradle, the idea forces us to confront a humbling truth. The cosmos might be far stranger and far more introverted than we ever dared to dream. What if the Big Bang wasn't the beginning, just the latest bounce in an endless cosmic game of ping-pong? Loop quantum cosmology dares to rewrite the origin story of everything, proposing that time doesn't start with a bang, but curves back on itself like a Mobius strip of reality. Picture the universe not as a one-time explosion, but as a cosmic accordion, collapsing and expanding over and over in a rhythm older than existence itself. This radical vision comes from applying loop quantum gravity, a leading theory to unify quantum mechanics and Einstein's relativity, to the earliest moments of the cosmos. Unlike classical physics, where the Big Bang crunches everything into an infinitely dense singularity, loop quantum cosmology suggests spacetime has a kind of quantum spine, a granular structure that resists infinite collapse. Imagine stretching a rubber band until it's taut, but instead of snapping, it recoils with enough force to fling the universe outward again. That rebound isn't just a theoretical curiosity. It could erase the need for a true beginning entirely, replacing it with an endless cycle of cosmic renewal. The math reveals something breathtaking. As the collapsing universe approaches the density of a black hole's core, quantum effects generate a repulsive force so powerful it halts the crunch in its tracks. Space doesn't vanish, it bounces, smooth and seamless, transitioning from contraction to expansion without a singularity. This means the heat death of one universe could literally be the Big Bang of the next, with no boundary between them. Time in this model isn't a straight line from past to future. It's a loop where endings and beginnings blur into one. Evidence might be hiding in plain sight. If our universe is a rebound, traces of the previous cycle could linger in the cosmic microwave background, the afterglow of our Big Bang. Some researchers claim to have spotted anomalous patterns in this radiation, concentric circles or unexplained temperature variations that could be bruises from a pre-bounce collision. Even black holes, those cosmic shredders of information, might not be in points, but tunnels where matter and energy slip through to seed the next cycle. It's as if the universe has a built-in recycling program where the remnants of dying stars become the raw materials for new creation. But here's the twist that bends the mind. If time is cyclic, then the arrow of time, the reason we remember the past but not the future, might just be a local quirk. In the moments before the bounce, entropy could reset, erasing the thermodynamic history of the old universe while preserving quantum correlations. That means the laws of physics might carry over from cycle to cycle, fine-tuning themselves with each iteration until conditions for life emerge. We could be living in universe number 7 trillion, riding a wave of cosmic evolution older than any calendar could measure. The implications shake philosophy to its core. No divine creator, no inexplicable singularity, just an endless dance of space-time, rising and falling like breath. Every galaxy, every atom, every moment of history might be a variation on a theme played infinite times before. So the next time someone asks what came before the Big Bang, the answer might be simpler than we ever imagined. Another universe and another, stretching backward into the eternal dark, a chain of cosmic resurrections with no first link and no last. Long before telescopes or particle accelerators, ancient cultures dreamed of the universe hatching from a colossal egg, a primordial womb where chaos cracked open to birth order. The Hindu Rigveda sings of the golden Hiranyagarbha, the cosmic egg floating in void's dark waters. Chinese myth whispers of Pangu stirring inside an egg until his limbs split shell into sky and earth. Even the Dogon people of Mali described a vibrating egg of the world that shattered into galaxies. These aren't just poetic metaphors, they're uncanny premonitions of a theory that's redefining modern cosmology. The universe as a quantum egg, its birth not a bang but a transition, from nothingness to everything in a single, seamless unfurling. Enter the Hartle-Hawking no-boundary proposal, where Stephen Hawking and James Hartle traded the Big Bang's fiery singularity for something far stranger. A universe with no edge in time, no sharp beginning, just a smooth, self-contained geometry like the surface of an egg. Picture spacetime not as a linear timeline exploding from a point, but as a distorted sphere where the Big Bang pole melts into imaginary time, a mathematical trick that erases the need for a singularity. In this model, the universe doesn't emerge from anything. It simply is whole and complete, with the Big Bang just one moment in its curved fabric. It's as if the cosmos hatched from its own potential, a self-fertilizing egg that needed no chicken, no creator. Just the quantum rules that let something emerge from nothing. The parallels between ancient myths and cutting-edge physics are too striking to ignore. Both imagine creation as a kind of symmetry breaking. The egg's shell fractures, releasing twin forces of order and chaos, while quantum fluctuations in the Hartle-Hawking model shatter perfect unity into the particles and forces we know. Even the egg's spherical shape echoes the universe's hypothesized closed geometry, where traveling far enough in one direction might theoretically bring you back to your starting point. And just as myths describe the yolk nourishing the newborn world, modern cosmology suggests the universe's initial uniformity. The near-perfect spread of energy in the cosmic microwave background might be the scrambled remnants of that primordial perfection. But here's where physics leaves myth behind. The Hartle-Hawking proposal isn't philosophy. It's built on equations that predict real, observable consequences like the universe's unlikely flatness and the specific spectrum of quantum ripples imprinted on the cosmos. If the cosmic egg model holds, those patterns are scars from the shell cracking, the moment quantum probability crystallized into classical reality. There's even a haunting implication for time itself. Just as an egg has no before its own existence, the no-boundary universe suggests asking, what came before the Big Bang might be as meaningless as asking what's north of the North Pole. Time, in this view, isn't a river with a source, it's a loop, with the Big Bang not the first tick of the clock, but the curve where the clock's hands meet. Perhaps the most poetic twist is how this theory bridges the oldest and newest stories of creation. When the Dogon elders spoke of the egg's vibrations, were they intuiting quantum fluctuations? When Hindu sages described the golden womb, did they glimpse the Higgs field condensing into matter? We'll never know, but the cosmic egg endures not as superstition, but as a symbol that some truths about existence are written so deep they echo across millennia. The universe might not have literal yolk and shell, but in the mathematics of its birth we find the same miraculous transformation from nothing, everything. From simulated realities to cosmic eggs, from black holes birthing universes to the universe itself being a vast, thinking mind, we've ventured into realms where science blurs with philosophy and the unimaginable becomes possible. Each of these 25 theories isn't just a wild guess, they're serious attempts to crack the ultimate mystery. Where did all this come from? Some suggest our existence is a fleeting quantum hiccup in an endless void, while others paint the cosmos as an infinite fractal, nesting realities within realities. There are theories where time loops back on itself, where consciousness shapes reality, and where the Big Bang was just one note in an eternal symphony of cosmic rebirth. Think about it, what's more awe-inspiring, the idea that we're living inside a black hole, or that every black hole in our universe contains another, that the stars above might be nodes in a galactic-scale brain, or that our entire existence could be a hologram projected from the edge of space. These aren't just thought experiments, they're challenges to everything we assume about reality. They force us to confront the limits of human understanding and ask, is the universe stranger than we can even conceive? And here's the beauty of it, none of these ideas are final. Science thrives on questions, not absolutes. Maybe one day we'll find proof that our cosmos is a simulation, or that we're riding the rebound of a white hole's explosion. Or maybe the truth is something so bizarre, so far beyond these theories, that it'll rewrite reality all over again. So now we turn it over to you. Which of these mind-bending theories left you staring at the ceiling at 3 a.m.? Was it the Boltzmann brains, the terrifying thought that you might just be a momentary flicker in the void, or the living universe where galaxies breathe and black holes think? Drop your favorites in the comments below. We want to hear which cosmic mysteries keep you up at night. And if you're hungry for more deep dives into the unknown, hit that subscribe button and ring the bell. The universe is full of secrets and we're just getting started. Until next time, keep questioning, keep wondering, and never stop looking up. The greatest mysteries are still out there waiting.